Welcome to the 67th Theoretical Physics Colloquium by Professor Dimitrios Psaltis, who's the chair of Theoretical Astrophysics program at the University of Arizona. He received his PhD at the University of Illinois at Urbana-Champaign in '97. He had several postdoctoral positions after that at Harvard-Smithsonian Center for Astrophysics, MIT. And then he got a 5-year member position at the Institute for Advanced Studies in Princeton, but he then moved very soon after that to a faculty position at the University of Arizona, where he remains since 2003. Since 2013, he's a full professor, and he is, since 2016, a chair of the Theoretical Astrophysics program at the University of Arizona. He is a member of 2 collaborations, member of the NASA's NICER mission since 2010, and a member of EHT, Event Horizon Telescope, since 2016. Over the years, he received a number of different awards and honors. In '97, Jordan Askew Fellowship at the University of Illinois, '97 Harvard-Smithsonian Prize, postdoctoral fellowship, 2005 academic prize of the Bodasaki Foundation, and a Senate Career Award in 2008. In 2016, Radcliffe Institute Fellowship at Harvard University. And finally, last year, he received 2 very important awards as a member of the EHT collaboration, Bruno Rossi Prize of the American Astronomical Society, and Breakthrough Award as well. He served in many capacities at different places, and as an example, he was on the Science Advisory Board of the Max Planck Institute in Bonn between 2013 and 17. His research interests include general relativity, black hole astrophysics, gravitational waves, black hole accretion disks, test of general relativity, physics of neutron stars, numerical methods in general relativity, and many more. And today he will be talking about tests of general relativity with black hole shadows. With that, I'll give the microphone to Dimitrios.
Thank you very much, Igor, for the invitation and for organizing this wonderful set of presentations and talks. I actually really enjoy watching them, either live or afterwards. And thanks everybody for coming today. We have a nice big group, and I hope everybody will be able to join with questions. As Igor said, please don't hesitate to interrupt. And there are 2 places in my presentation where I have put some blank slides where I will take a quick break in case everybody wants to speak up. So let me share my screen, and hopefully everybody can see it here, and start my presentation today, which is about testing general relativity with black hole shadows. And of course, this is something that we used to only talk about it, but this is something that we can actually do now with the results that are coming out of the Event Horizon Telescope, this new remarkable project of which I have been a very part of since the very beginning, that allows us to actually take for the first time pictures of black holes at horizon scales. Now, this is a theoretical physics colloquium, so I'm going to focus almost entirely on the theoretical physics aspect of it, on testing general relativity, how we do it, why we believe it, what are the results, and how do we affect our understanding of physics. But I suggest that you Google on the web and find other presentations, either by me or other people, to talk about the project itself, because it's a remarkable technological achievement, and more than 300 people involved in every single aspect of it, from building telescopes to actually turning them into real science. So as I said, today I'm going to focus on one tiny aspect, but one that is closest to my heart of this project, which is how can we use these images of black holes, and this is the famous first image of the M87 black hole, to say something about the theory of general relativity. And I will start by taking first a step back and ask, what is it really about general relativity that we're interested in? Because I'm sure you've all heard many talks, and you've seen many announcements that every single time general relativity has been compared to data, it always has remarkable agreement. So you might be asking yourselves, why are we beating on the same dead horse, right? Why are we keep on asking ourselves, is general relativity the complete theory of gravity? And to answer that question, as I said, we take a step back and we first think of the fact that general relativity, or any theory of gravity for that matter, comes with two separate but connected ingredients. Even Newtonian gravity comes with those two separate ingredients. One of them is the part of the theory that it's Einstein's field equations in GR, or Poisson's equations in normal Newtonian gravity, that effectively allows you to calculate the gravitational field, or the spacetime if you want, in the presence of matter. If I put the sun in the middle of flat spacetime, how does it curve the spacetime itself? But then you have a completely separate ingredient that in both cases is called the equivalence principle, that allows you to calculate the trajectories of particles, primarily test particles and photons, in the presence of that external gravitational field, in the presence of that curved spacetime. So as I said, there are completely different sets of approaches to test those two aspects of the theory. And what I'm going to talk about today is talking entirely about testing Einstein's field equations. In everything we'll do, we will assume that the equivalence principle is satisfied, and we're trying to figure out how much does a particular distribution of matter curve the spacetime itself. Now, you might say, you know what, the equivalence principle is really the beautiful physics, right? Einstein's happiest thought. This is the intuition that changed our ideas of gravity from a field to a geometric theory. The fact that everything follows straight lines in a curved spacetime. Do we really learn anything other than, epicycles when we talk about Einstein's field equations? Maybe there's a factor of 2 in front, maybe there is an additional little, R squared term. Is there something really fundamental that we're after by looking at Einstein's field equation? Because the equivalence principle, I think we will all agree, it's something that is really fundamental. And even though it was not known at the time by Einstein, and actually he kind of reverse engineered his field equation to go through the data, we now know that indeed that field equation encompasses something really fundamental about the space and universe itself. And that's due to a number of theorems by Lovelock and Grigor that demonstrate that if you make a small number of very, very basic and universal assumptions, the fact that we live in 3+1 dimensions, that our theory is local, that our theory is of second order, and that it only involves the metric with no additional fields, so just the metric is the only gravitational field, then Einstein's field equations are unique. And this is remarkable because what that means is that if you find any modification, any need for modifications, not quantum, this is at the classical level, modifications to the field equations, one of those 4 assumptions needs to be thrown out the window. And these are really significant and remarkable assumptions about the universe itself. So in my mind, testing the field equation is as fundamental as it is testing the equivalence principle. But of course, this theorem also not only tells us something qualitative like that, but also shows us a way to how would we go around modifying general relativity. Well, you just need to modify one of those assumptions. So you can make modified gravity by going to higher dimensions other than 3+1, making it non-local, adding higher order terms, or adding different field contents, adding scalar fields, vector fields, tensor fields, couple them together and whatever else you want. And this is actually a really beautiful, old by now, slide by Tessa Baker, who is in the UK now, the University College London, where you can actually take any single proposed modification to general relativity and put it in that idea, put it in that parameter space. Some of them modify one, some of them modify more than one of those assumptions, but in principle, take your favorite modification to general relativity, and you will always find out that it boils down to modifying one of those 4 assumptions. So because it is an enormous set of modifications, we do not have a unique way to keep on adding terms, and very quickly it becomes very complex. What we decide to do in this field when it comes to testing relativity with black holes is to not start from a fundamental field equation, but start more importantly, more closely to the data by something more phenomenological, let's say a parametric modification to the metric. use the experiments to put constraints on the modifications to the spacetime or the dynamics of the spacetime, and then hopefully if we find any of them, then look back and ask ourselves what would have been the fundamental theory that would give rise to that. And in some ways, this is exactly what people do in cosmology, in a sense that you fit the data assuming an equation of state for the dark energy. And then if you think that this is modification because of modification to relativity, you look back what kind of modification to the field equations will give rise to that empirical effect. No matter what, any modification will require a violation of one of those red fundamental properties of our understanding of spacetime. So, okay, this is what we're going to do, but have we not killed, as I said, have we not killed any possible modifications to general relativity and the field equations? And what I want to point out with a number of slides now is that it depends on what question is it that you're really asking. So for example, when it comes to putting all the astrophysical objects in a, what I call the parameter space of gravitational tests, and here in the x-axis is the potential that is probed. This is really the Newtonian potential, but you can define it in a way that is covariant using redshifts at infinity. This is the Newtonian potential in units of speed of light squared probed by different astrophysical objects. And the y-axis is the curvature of the gravitational fields, gm over r cubed. This is the fundamental quantity in Einstein's field equations. This is the energy density, if you want, in the gravitational field. And you will see that you have an enormous range of scales, 10 orders in potential, 40 orders, 50 orders in curvature. And you can put here the probes formed, the tests probed by stars, pulsars, solar system objects, satellites around the Earth, white dwarfs, neutron stars, stellar mass black holes, supermassive black holes, the stars that are orbiting the black hole in the center of the Milky Way, galaxies, the rotation curves of galaxies, clusters, the cosmic microwave background peaks, and so on and so forth. So you see, this is the enormous range of gravitational fields that we can probe in astrophysics. And now you ask yourself, where have I tested general relativity here? Because I don't know a priori what where the modification will show up. Will it be in potential? Will it be in curvature? Will it be in acceleration? Will it be in length scale and mass scale? So we have had for since the beginning of general relativity really high quality tests in the solar system, at the surface of the sun, with Earth satellites and with the inner planets. We have had really remarkable tests of general relativity with pulsars, double pulsars, and the double pulsars are orbiting each other at the radius that are more or less the size of the surface of the sun, and that's why they probe quite similar gravitational fields. We have had a lot of tests with cosmology, cosmic microwave background, expansion of the universe, and so on. Very recently, we started getting tests with stellar mass black holes with LIGO and Virgo. The Nobel Prize of this past year, probing gravitational effects with the orbits of stars in the vicinity of the Milky Way. And what the Event Horizon Telescope comes is to fill this parameter space by probing supermassive black holes. These are the curvatures for massive black holes that are similar to the curvatures probed by solar system tests, but at a gravitational potential that is comparable to that of the LIGO sources. So it is practically an orthogonal constraint in what we have had before, when seen entirely from the point of view of what is the strength of the gravitational fields that they probed. And I just point out again how enormous the ranges are. We know that general relativity is in agreement with the data in the solar system test to within 1 part in 10 to the 5. I think any theorist that deserves being called a theorist, and most of you here are, will have a trivial way of making a modification that becomes of order unity when I increase the potential by 6 orders of magnitude, or if I change the curvature by 10 orders of magnitude, right? Even a linear deviation will be completely hidden at the solar system test, but will cause order unity deviations where we're looking at. This was the original motivation of why we want to fill this parameter space, probe everywhere and see how well we can test general relativity, and the Event Horizon Telescope poke somewhere that we have not poked before. But that's not all of it. This is not the only way to test the difference between tests of general relativity. I'm going to throw them here in a completely different way. I just put them random words: expansion of the universe, structure formation, pulsar evolution, black hole gravitational waves, Shapiro delay, shadows, solar system. Why did I throw them like that? Because you can realize that some of those systems involve the coupling of the gravitational field with matter. Some of them are just pure vacuum tests. And if you really want to test the coupling, then the blue ones won't matter and vice versa. Some of them involve stationary asymptotic metrics at infinity, and some of them involve dynamics, right? Gravitational waves involve dynamics of the theory, the expansion of the universe and the evolution of perturbations involve dynamics of the theory. And you can design theories that have the same asymptotics but different dynamics and vice versa. That it is very easy to make all the theories have the identical vacuum solutions but different matter solutions, and so on and so forth. So we really, since we are going fishing here, we don't have a good reason to know which way the modification is going to be. We want to cut this enormous parameter space of possibilities in any single possible way that we can to figure out, do we see a smoking gun of something going wrong? And of course, with the black hole shadows, these are enormous black holes that have lived through the age of the universe. The space-times that we're going to be probing are purely stationary. But even in that case, I will say that it's not trivial to say what is it that we're looking. And let me make that example. Let me push that example a little more for you to understand why we're doing what we're doing. So I just wrote here the metric in a more general form of a spherically symmetric object, right? It has diagonal components, time, radius, and this is just the d omega, the angular part, r square sine square theta. And I allowed for a little frame dragging in T phi. One of those components measures the slowing down of clocks, right? This is the warping, warping of the time part of the space-time. And for example, in the solar system, you probe it only with the precession of Mercury, with the precession of orbits. None of the other tests that you're doing probes the TT component of the metric. The RR component of the metric, which is warping of space, you probe with the deflection of light and the Shapiro delay. And you see now we have two different experiments in the solar system with the exact same gravitational field, and yet they probe two different directions of warping. So if you want to do it at a phenomenological point of view, not as a fundamental theory, then those two tests probe completely different aspects of the space-time, which is why they're important to be done simultaneously. The R square, of course, nothing but space-time dimensions -1, and of course you would have more elements of the metric. And the frame dragging, the T phi components measures frame dragging, and you probe that with things like Kraft probe B or the lunar ranging. So when we say we want to test general relativity, we really need to put, or general relativity has been tested, we really need to put a very long list of bullets about what aspect of general relativity, at what gravitational fields, with what objects, matter dynamics, vacuum or whatever, and even that, what aspect of the metric or of the space-time is it that we're really probing. And that's why we need a very, very large number of those tests in very, very large number of situations. And until now, how have we been doing this test? Because a lot of those tests took place in the weak field. What you do is you write your space-time. This is your Schwarzschild space-time in particular coordinates. And the ones that, this term here, the 1 minus 2gm over rc squared is really Newtonian gravity. And then the terms that are highlighted here are additional terms. This term is 0 in general relativity. This term here is 1 in general relativity. You stick parameters in front, betas and gammas. We don't believe those betas and gammas are universal functions, right? Because they depend on what field provision I was talking to you about you're doing. But you effectively try to measure what those betas and gammas are in the solar system, and you want them to be as close to 1, because 1 is what they need to be for general relativity. Then you take all your observables, the deflection angle of the ankle, you write it as a function of gamma, you compare it to the data, and this is a nice compilation as a function of year of the experiment for deflection of light and Shapiro time delay constraints. on that gamma parameter. And you see now we're about 1 part in 10 to the 5 and 1 part in 10 to the 4, depending on different ways that we're measuring that exact same parameter. And of course, those here in the red are the initial Eddington measurements from the solar eclipse. So this is what we have been doing so far, but this is not something that we can continue doing when it comes to black holes, because with black holes, we cannot really do a small expansion in M over R, because we are at M of order R, we're looking at things close to horizons, and therefore we need to come up with a slightly different way of effectively doing these kinds of metric tests of general relativity. And before I stop, I just want to put this up and then we'll take a little break for a short question or two, is in particular, when we're dealing with black holes, there are 3 fundamental and important testable properties of black hole spacetimes that we're after. In general relativity, there's something called Birchhoff's theorem that says the spacetimes of any object, with matter or without, therefore the sun and a black hole, will be Schwarzschild, will be independent, it will be the same, no matter what the properties of that object is. And therefore, when we compare solar system tests, and we say it's close to Schwarzschild, and we compare to black hole tests, at the limit of very small spins, we better find that both types of objects have the exact same spacetime. The second important aspect of black hole properties in general relativity is that they are scale-free. Remember, general relativity is the only theory in physics that does not have a scale. And I'm not counting the Planck scale, right? It's the only theory where it's completely scale-free with mass. And therefore, unless I put matter in it to introduce some scale, like the mass of the object, or spin or whatever I want for the object, the properties of the black holes are completely scale-free as long as you scale all the distances with mass. So if we compare LIGO black holes, which are 10 solar masses, 30 solar masses, to Event Horizon Telescope black holes, which are million and billion solar masses, they better have the same spacetimes. And the third part is the no-hair theorem that says that in general relativity, black holes vacuum spacetimes that are surrounded by horizons are uniquely described by the Kerr metric, and therefore they can only have the mass and the spin as their independent parameters. So these are 3 guiding aspects of black hole spacetimes in general relativity between black holes and other objects with matter that we are aiming to test in order to see, is there any smoking gun that tells us that the field theory of general relativity needs to be modified. So I'm going to take a quick break here and ask if anybody has a question.
I have a naive question.
Go ahead.
You wrote a metric, but it is not Schwarzschild metric. In Schwarzschild metric, there is a correction to GTT and GRR, right?
Good point. I tried to throw it under the rug really quickly. I wrote it in what they're called aerial coordinates. So it's Schwarzschild coordinates. So there's an R squared d omega here, not in isotropic coordinates. In these coordinates, there's no correction in GTT. If I write it in isotropic coordinates, then there is a correction. And that's why GTT only has a beta, and that gamma comes from the coordinates transformation from the GRR, actually.
Okay.
Yeah. There is a reason that I do it like that, as I will show in a second. The size of a black hole shadow seems to depend almost entirely on the TT component of the metric when written in aerial coordinates. And that's why it allows us to understand what determines that black hole shadow size.
Okay.
Thank you.
Hey, Roger, do you have a question?
Yeah, thank you. This is Roger Windhorst. So do supermassive black holes acquire any net charge, electrical charge that matters in the formalism?
So that's a very good question that people have thought a lot about it, because of course a charge is the other hair that is allowed in general relativity. There are a lot of hand-waving answers from the fact that because all those black holes that we see have charged plasma around them, and that's the only reason why we can see them, as you will see in a second. And therefore, if the black hole had any charge, residual charge to begin with, it would very quickly attract the opposite from the plasma, neutralize and be done with that. And you can show that the time scale for that is extremely short. But this is the only place where, the only type of argument that people have done. We haven't found any evidence for that in any other form, in any other dynamics or any other part of the, spectra or astrophysical aspects of black holes, and we're sticking with this.
Okay,
Also
thank you.
magnetic charge, by the way, if there are monopoles.
True.
then there is also magnetic charge we have, and there
Correct.
is no magnetic plasma. So.
Correct. I will talk a little bit about charged black holes in a second, and we throw them all as additional charges and we try to constrain them. Mm-hmm. And those charges can be true electromagnetic, electric charges or magnetic monopoles, or they can be any other vector field mm-hmm. that behaves as the presence of an additional charge. And this is something that we can now constrain from the size of the shadow and the properties of the shadow.
Okay, next question from Harry Adhikari. Can you ask it yourself? I could probably read it because I think he's muted. There is a question. It means our solar system might be inside a huge black hole, right? That's the question I'm reading.
Sorry, what was the question? I didn't understand it. It means that?
Does it mean that our solar system might be inside a huge black hole?
This is a different question. If the entire universe is inside a big black hole, right? And this comes back from those coincidences, if you want, that, the size of if you take the size of the Hubble volume and you calculate the size of the horizon of all the interior mass, turns out to be the size of the Hubble volume. In my mind, all of that is just a consequence of the fact that there's no scale in general relativity. So, everything scales with m, so everything will be of order unity different than m. Same reason why Newtonian size of a black hole, even though it's completely wrong physics, is the same size as the general relativistic size of the black hole. This is just dimensional arguments, but I don't know of any testable consequence of, if we're all inside someplace else.
Okay, I think we exhausted all the questions at this moment.
Thank you. So let's move on and now bring it back to where we wanted to start. The Event Horizon Telescope. How do we take those pictures of the black holes? And as I said, I'm going to say nothing about this. Please go look at other presentations, because this is an entire presentation by itself. But the Event Horizon Telescope is this really technologically remarkable array of millimeter telescopes in places all around the Earth, because we're really trying to use as much of the Earth as possible. The biggest baseline distance between telescopes determines the resolving power. And we have telescopes from Hawaii on the east to, this is in 2018 now, to the mountains over Granada. You can actually see them from the Alhambra in Spain, and from the Greenland, northern part of Greenland, the Greenland telescope, all the way down to the geometric South Pole, where you put all telescopes, you observe simultaneously the black holes, two main black holes, the one in the center of M87 galaxy and the one in the center of our own galaxy. You take all the data, you transfer them to a big correlator, you run them through the interferometric pipelines. And after a lot of hard work and a lot of things that I'm not going to discuss, you end up with the image that you've already seen. And this is the image in the black hole, in the M87 black hole, the one that we announced a couple of years ago. And it has a number of characteristics, and we're going to focus on a couple of them for the purposes of what we are going to do today. I'm not talking about the accretion, I'm not talking about the plasma, I'm talking only about the gravitational fields. And one thing is that the image itself looks like a ring. It has a big depression in the center, a brightness depression in the center. And we have identified this depression as what I will define in a second to be the shadow of the black hole, the silhouette of the black hole and the surrounding emission. This ring that you see around it, it's artificially broadened for reasons that have to do with the way that traditionally those radio observations are done, but it is relatively narrow ring of emission that quasi-circular that surrounds the plasma. And there is a little bit of north-south asymmetry is fainter in the north, brighter in the south. Don't worry about those blobs here. These are practically artifacts of the particular place where the telescopes exist, but the north-south asymmetry is real. You can actually see directly in the data. And the way that we understand the north-south asymmetry is Doppler effects, because there is a big jet of this black hole that's moving east-west here. And if you have matter orbiting around the spin of the black hole or the spin of the accreting plasma, the bottom part is pointing towards us, so it's Doppler boosted. The north part is pointing away from us, is Doppler deboosted, and that's what we think causes this asymmetry. But as I said, now we have observations of polarization, magnetic fields, variability, and so on and so forth. I will not focus on any of that. I will focus entirely on what do we learn about the gravitational fields from the fact that we see this narrow ring of emission surrounding a big depression. And this is something that we've been calling the black hole shadow, and not necessarily the best term, but this is, for historical reasons. And people have been talking about black hole shadows for many decades, pretty much before, like just after I was born. Bardeen and Luminet have been trying to understand what would be the observational appearance of a black hole if somebody, in the far future, would ever be able to take a picture of it. And actually, this is a wonderful image calculated by Jean-Pierre Luminet, and it was actually done by hand. It was before computers could do actual images like that, but calculated completely. But remember, this is the 70s, and this is at the time where people thought that really that black holes are going to be accreting matter from extremely thin accretion disks, what they're called the Thorne-Novikov or Sikorsky-Yaev accretion disks. And the idea, and those accretion disks will actually have a hole at the location of the innermost stable circular orbits where everything is going to be plunging. These are really early ideas now. And what Luminet was calculating was what would an observer at infinity see? They will see a primary image, which is the thing that you see in the bottom. You will see a secondary image, things that are underneath or above that are gravitationally lensed around the black hole. You will see a shadow in the center, perhaps the location of the ISCO, and this tiny little ring of emission here. Now, these were wonderful ideas at the time, but it turns out that they're not useful. They were not useful in either helping us design the Event Horizon Telescope, nor in understanding the properties of the Event Horizon Telescope. And the reason is that, for example, for the case of M87, if this was the case, you would ask yourself, what is the temperature that matter would have had if it was accreting from this kind of accretion disk, and where it would emit? And if you run it through the numbers, you will realize that the temperature is such that it would have emitted at the UV at about 13 nanometers. Remember, the Event Horizon Telescope observes at millimeters, very, very different wavelengths. And if this was the true physics of the shadow, then we would never have been able to observe it. More importantly, because there is such an enormous absorption extinction from everything between us and the black holes in the UV that we would never be able to do the experiment. Something else happens in the black holes that allows us to take those pictures. And this is why the picture that we took looks actually very, very different than the picture that you see here, or if you like movies, the picture that you saw in Interstellar. And what happened is that sometime in the mid-90s, based on different other astrophysical aspects and spectra of those sources, it became obvious that these are not geometrically thin accretion disks. They're very radiatively inefficient, those plasma modes there. And because they're so radiatively inefficient, they heat up to virial temperatures. And because they heat up to virial temperatures, they puff up. So you have what we call more or less optically thin, which means very large mean free paths between photons and particles, puffed up, extremely hot virial temperatures, GeV, accretion flows around the black holes. And there's a work that we did back in 2000 with Feya Lozal and Ramesh Narayan, back when I was at Harvard, when we started calculating what would be the observational appearance of those black holes had we taken an observation. And the emission mechanism that matters at radio wavelengths, this is what you would have seen at the centimeter, is self-absorbed synchrotron emission. Magnetic fields, plasmas, pure synchrotron emission. And this is now a calculation later on by our colleague C.K. Chan here in Arizona, where you can actually do it with full numerical simulation. And what you see is that if you were to observe at the wrong wavelength, then self-absorption, the fact that the photon mean free path is actually in those particular wavelengths is very small, does not allow you to see the black hole in the center. You just see a big fog around it. But the benefit of synchrotron emission is that it has an extremely strong dependence on frequency. And as I crank up the frequency, it will become more and more transparent. So I will play a little movie for you. By increasing the frequency, decreasing the wavelengths to 1 millimeter. And if you pick the wavelength right, and that's why we picked the 1.3 millimeters for the EHT, then all this fog becomes transparent. And what you see is you see just enough light, just enough photons to come out close to the black hole. And on top of that, you see that, I will show that a little better in a second, you see that shadow, the silhouette that the black hole generates in the surrounding emission. We did that in 2000 because in 98, so this is from the original paper now, in 98, there were 2 measurements for the black hole in the center of the Milky Way for the size of the black hole image as a function of wavelength. And those lines with Maxwellian and non-Maxwellian electrons are the predictions of that particular model of virial geometrically thick accretion flows. And they were going indeed through the data, and at around 1 millimeter, they were generating sizes. The models were predicting sizes for the image of the black hole that were comparable to the size of the black hole shadow, which is about, the diameter is about 10 m. And it is for lensing events that will come up in a second. And this is why we put together the Event Horizon Telescope to observe at millimeter wavelengths, and we were expecting to see this particular type of feature. So what is the shadow in this particular case? And to discuss that, I want to remind everybody about a couple of quick things regarding the black hole spacetime. The fact that there are 3 characteristic radii outside the horizon of a black hole. And here I plot them as a function of black hole spin. Solid are for prograde motion, dust are for retrograde motion. The event horizon we all know, it's 2 gravitational 2m, non-spinning, 1m for spinning. The red is the innermost stable circular orbit. This is the radius where if you're inside which you do not have stable circular orbits, and if you try to put something in orbit there, it will plunge to the horizon. But the one that has until recently taken much less attention to is what is called the photon orbit, which goes from 3m to 1m, depending on the spin of the black hole if it's prograde. And the photon orbit for a spherical spacetime, Schwarzschild spacetime, is the distance at which if I send a photon tangential to the radius, it would make a perfect circle, a place where even photons orbit. Now, what happens if I spin up the black hole? It turns out that the Kerr metric allows spherical photon orbits. So this is not circles anymore, but the photons, these are trajectories of photons at 2 different black hole spins, 0.4 and 0.9. And the Kerr spacetime allows, actually many spacetimes you can show, there's some beautiful theorems proven recently, allow for photons to orbit at a particular radius. And it turns out that it is the size of the photon orbit, gravitationally lensed to an observer at infinity, that determines the size of the shadow of the black hole. It's not the horizon, it's not the ISCO, but it's the gravitationally lensed size of the photon orbit. Why is that? By the way, this is a beautiful animation by Leo Stein, and you can go to his website and you can play with all the parameters. That's where I took it out from.
All these trajectories
Yes.
are unstable or not?
They're all unstable
Circular.
orbits.
All unstable. Okay.
All unstable orbits, and that's important, as you will see in a
thank
second.
you.
So why does that affect what we see? So I'm going to give you 2 animations, and then I will show some full simulations in a second. So what I have here is a black hole, Schwarzschild black hole, seen from above, right? So this is the, I mean, it doesn't matter, but think of it that this is the equatorial plane of the black hole. And this black line is going to be the trajectory of a photon that treats an observer at infinity at the bottom, the photon path. Red is the horizon, and blue is the radius of the photon orbit. What I'm going to do now is I'm going to change the impact parameter of the photon path. I'm going to move the photon path to the left and to the right. But remember, this is a backwards impact parameter, right? These are photons that say emitted from here and go to infinity, right? I'll show the little movie first, and I will stop it. You see the effect? Oops, sorry, the zoom, I think, flipped a little bit. I will show it in a second. For some reason, Zoom does not like to show the, okay, let me stop it. It doesn't show the interesting aspect of it, the different impact parameters. So red impact parameters, black impact parameters, and green impact parameters. Because this is optically thin emission, transparent emission, what you see at any impact parameter is the integral of the photon, of the path of photons, of the emissivity of photons along that photon path, right? And if I have a small enough impact parameter, and suppose that I have a lot of plasma here, then I will get a relatively small photon path, because very quickly, if I trace it backwards, those trajectories hit the horizon. And of course, I'm further out from the horizon because of gravitational lensing. If I go to the green photon path, you will see here more gravitational lensing, like it changed by 90 degrees, but I get some significant photon path. But there is that critical curve such that if I trace it backward, I become tangent to the photon orbit that introduces this incredible fanning of the photon paths. And now every emission that has generated in the right direction anywhere in those black trajectories will be focused on that critical photon path. So effectively at that critical impact parameter, I pick emission from my entire space. And actually at the critical impact parameter, you have infinite emissivity because it's an infinite, but very close to that, I pick an enormous emission from around there. And let me show you how that works if I put some plasma to it now, not just trajectory. So this is an image of a black hole. And what I have here on the left is a cross-section of the brightness of the image. So, 0 is the center of the black hole. This is the critical impact parameter, and then further out. And what I have here is a vertical cross-section of the accretion flow. So this is a thick accretion flow. And the yellow is one of those trajectories. So what I'm going to do now is I'm going to make that trajectory move left and right and see what it corresponds to the image. When I'm looking far away, like out here of the image, I just cross a little bit of the accretion flow, right? And I get some material. But when I come to the point where I start getting multiple crossovers and I get multiple crossings of the material, then I get this big emission peak. And of course, this is the critical impact parameter, where in reality it's infinite, but I just cut it for numerical reasons. And this is why when you look outwards and you take the image of the black hole, you see this bright peak of emission. This is Doppler shifted now, so it's not very, this is the bright part, this is the less bright part, but effectively being extremely close to that critical impact parameter, which is what we call the black hole shadow, and a big suppression in the end. And I can pick out, just as I did before, a couple of characteristics. The A impact parameter is here. You see, you pick emission in that solid part of the accretion flow. As you get closer, you pick a little more emission because the temperature increases. By the time you hit the C impact parameter, you're dead in the peak there, because now you have both sides of the emission of the accretion flow emitting. D is the critical or close to the critical. You start making 3 and 4 and 5 and 6 and 7, but they're not individual rings because, of course, they're significant breadth, and so they're all the rings, all the things overlap. But effectively, what you get is you get within a very small range for the critical impact parameter the bulk of the emission, which is why all the images look like rings surrounding the black hole shadow. And the black hole shadow here is defined as the critical impact parameter. So we do that not only with simplistic models, but we actually throw full general relativistic magnetohydrodynamic simulations, time dependent, on our black holes. And this is from one of the original EHT papers. And you get a lot of fluff. Depending on the spin of the black hole, you get the critical impact parameter here, but we don't have the resolution to see any of that. If you take those images and smooth it out at practically at the nominal resolution of the image, you see exactly what we observe. A narrow ring of emission that is very close to the black hole shadow with the asymmetry that we expect. And I just want to point out that even though this is something that we did for a small number of papers, models in 2019, it's been almost a decade of a lot of significant work, people trying to understand the effects of plasma physics onto the images of the black holes, GRMHD effects and time variability for more than a decade, the presence of non-Maxwellian electrons, different magnetic field configurations, and now more recently, different plasma effects and even different space-time geometries. And no matter what, there are some situations where you, as I showed before, that you can actually block the entire image if you observe in the wrong wavelength or you put too much matter or whatever. But every time you have narrow rings of emission, those narrow rings of emission are always very close and surrounding the black hole shadow. And this is significant because the black hole shadow, that critical impact parameter, is an extremely clean gravitational effect, right? It's the gravitationally lensed size of the photon orbit that depends only on the metric and on nothing else. So I think we didn't start until 10 past, right?
Yes.
Okay, so I'm just freaking out a little bit about time, but I will, I will keep on that. And when we first started doing this, following this idea, we originally actually thought that we were going to be able to measure spins of black holes, because the minute you spin the black hole, we expected, like everything else, you know, this is just intuition from the Earth, we expected the shadow to start becoming more and more oblate. And we were for a surprise about 10 years ago, because this is now I threw away all the plasma, this is just the outline of the shadow of a black hole for a zero spin. When we started spinning the black hole, we didn't seem to become oblate. And unless you hit really, really high spins, like 0.995, we don't expect it to be like that. The only thing that we found is that the shadow, even though the center of the black hole is always at 0, 0, the impact parameter, the shadow outline remains a circle and just gets displaced towards the direction of the spin. And that was horrible news for measuring the spin of the black hole, because we don't know exactly where the black hole is to begin with. That's the only thing that we measure. And it's the same size, it's a circle, but it's great for something else, because that means that not only is the shadow a clean gravitational effect, the radius of the shadow is an extremely precisely predicted property of the black hole that is practically independent of the inclination with which you observe the black hole or the spin of the black hole. It is 5 gravitational units, the radius, 10 the diameter, give or take 4%. And that means that that allows you to make a null hypothesis of test of general relativity, because if you know the mass of the black hole otherwise, then you can predict the size of the shadow, give or take 4%, no parameters to fix, no parameters to change. It is either what you predicted or it's not. But we're a little concerned about that, so we wanted to understand why the heck does that happen? Where is my oblateness that I expected to say? And this is some wonderful work with my former student, Tim Johansson, where we realized that when you spin a black hole because of the O'Hare theorem, there's only, you can change simultaneously the effects of frame dragging, which is the off-diagonal components of the metric, and the effects of the quadrupole, which is the diagonal components of the metric. And on the left, I'm going to show you what happens to the shadow if I only change frame dragging, and I have removed the differential rotation. So it becomes prolate. So frame dragging, which has a cylindrical symmetry, would want by itself to make the shadow prolate. But the quadrupole has a quadrupole symmetry and tries to make the space-time, the shadow oblate. And it turns out that if and only if the space-time quadrupole is equal to minus spin square, which is the O'Hare theorem of black holes in the space-time, the two nearly cancel out and leave practically a tiny degree of asymmetry and a small displacement of the black hole shadow. So the fact that the black hole shadow has the same radius and a near circular space shape is actually a direct prediction of the no-hair theorem. And we have made, I don't have time to show here, but we have made a lot of spacetimes that we change separately the quadruple with the spacetime, and we can get all sorts of shapes and sizes, and I will show some in about a second. Oops, actually, I think this was my second thing, and we have about 10 minutes left in the presentation. How do we apply all of that? So any questions for people?
Okay, questions? Let me ask a quick question.
Other magnetic fields and some synchrotron radiation. So you discuss photons as if they just move by geodesic emitted at some point.
Correct.
But if it is synchrotron radiation, they emit it along the whole path coherently, or some piece of the path, at least close to the circular orbit.
So it won't be coherent. The wavelength of the photon is a millimeter, and the size of the photon orbit is the size of our solar system, like the radius of Pluto, like the orbit of Pluto.
That's not correct, because ultra-relativistic electron moves by the same orbit as a photon. So they can keep being coherent even if they move kilometers.
Correct. You can, I mean, this is something that you might have in case of a pulsar, for example. Mm-hmm. You can demonstrate that you do not have significant coherent emission in our cases. The other effect that one might worry a little bit about is birefringence, because of the presence of the magnetic field. It is not significant to cause, index of diffraction issues. The plasma frequency is significantly away from where we're observing. So you can actually use the geometric optics non-coherent emission relatively without worrying too much about here. Yeah.
So I just want to make sure I understand the main idea. So if you can quickly go back to the plot where you had the green, black, and red impact parameters. It's around there.
Yes.
Yeah, that one. So I just want to make sure I understand. I've never seen this before, so I apologize.
Sure.
But so it's kind of clear to me what happens if I think of those lines as photons going into the black hole. Mm-hmm. But if I think about photons going out of the black hole, I just want to make sure I have the right understanding. So if I look at the black region and I think about these photons as going out of the black hole, it seems to me that there is a region where photons are kind of focused into a narrow outgoing orbit. Is that the right way to think about this?
Correct. So the way that I like to think of them is, even though these are photon trajectories, is think of them as photon paths, in the sense that if you ask yourself, what is the brightness, like the number of photons that come out, at the edge of that black impact parameter, the way to calculate is that you follow each one of those photon paths. So say you're here, and you ask yourself how many photons from this point are emitted along that direction. And then you integrate along the photon paths. Mm-hmm. And then when you do that integral, it's the radiative transfer equation or the photon kinetic equation, then you calculate the total number of photons that come out. And what that shows is that this narrow range of, as you said, this narrow range of impact parameters has taken photons from anywhere here and collimated to that really, really narrow level. This is the critical impact parameter is where it becomes very big.
And that explains why we have that bump in the brightness, right? That bump corresponds to that black line.
So there are two bumps. So there's this bump that is the critical impact parameter. And then you have this other bump, which is kind of the green before. So if I would play it again, when you start making, you don't have to get an infinite number of fanning, but you need to get significant degree of gravitational lensing. Mm-hmm. And you start picking a lot of photons from all around the accretion flow, not just underneath you. And that's what determines the big pump of emission.
Okay, great.
But by definition, because you want the lensing to be extremely large to be able to see more of the emission, this happens always extremely close to the critical impact parameter. And it's indistinguishable from what we do with the EHD.
Okay, awesome. Thank you.
Continue then. How do we do that? So remember, we do not see the shadow itself. We see the peak of emission, the brightness peak of emission from the image. And we can measure it directly from the image, which is a higher order product, or we can measure it directly from the interferometric data. Don't worry about that for right now. But that peak of emission is a proxy for the location of the shadow. As I said, it's extremely close, but not necessarily on the location of that shadow. The difference is not more than 10–15%. So this is at most the highest mistake that you can make. And actually the difference is never bigger than the width of the ring, right? Because you know that the shadow cannot be disjoint from that. So we calibrate that proxy using a very large number of simulations just to see whatever we throw, how much would it be? In principle, it's closer, but we wanted to be careful about that. And we compare to the predictions from the Kerr metric, which I said is 5 ± 4% m, but you need to know a priori the mass of the black hole from infinity, from stellar dynamics. This is going to be superb for the mass of the black hole in the center of the Milky Way because we know its mass within a fraction of a percent. But for the one in M87, we knew the mass, and therefore we can make a prediction for the shadow diameter with two different techniques, one based on stellar dynamics, one based on gas dynamics, and we didn't know a priori which one of the two was the correct one. There was a lot of reasons why we preferred the stellar dynamics. Stars are test particles, gas is not. You have non-geodesic, like non-inertial forces that affect their properties. But when we asked ourselves, how does the prior knowledge of the prediction of the shadow diameter based on the stellar dynamics compare to what we actually measured from the EHD, it turns out to be exactly what one expected. And you can connect that into a fractional deviation between the two. If you pick the stellar dynamics, we got what we observed what we predicted, give or take 20%. If we were to assume the gas dynamic mass, it would have been off by a factor of 2. As I said, this is not going to exist for Sagittarius A star, the black hole in the center of the Milky Way. We have only one mass that is extremely well measured. But in this particular case, you have two options. One is to believe the stellar dynamics mass, which was a priori more believable to begin with, and use that as a test of general relativity, or believe the gas dynamics mass and now have to make a factor of 2 difference in your metric in order to account for it, and we chose to pick the first.
Okay. A quick question on
Go
the
ahead.
picture. Show the picture, please. The red curve is a little bit shifted from blue.
By
So
factor of 2.
So it is not just resolution, right?
Oh, no, it's not resolution. So the blue curve is the prediction based on the prior knowledge of the mass, assuming following the orbits of stars.
Theoretical prediction.
And this one is the prediction with the prior knowledge of mass following that you model the gas dynamics of the flow around the black hole.
It's not correct, yes?
I mean, so one can definitely say that if you believe in general relativity, clearly the stars measured the correct mass of the black hole, or backwards, if you believe the star dynamics masses, then general relativity has to give the correct prediction to within 20%.
No, I don't understand. So the red curve says measurement. It is measurement with resolution, right?
It is.
What is the red curve?
Oh, hold. The red or the purple? Because there's a red here.
No, the purple.
The purple. No, the purple is the measurement of the shadow within the resolution of the EHD. Yes.
Okay.
Sorry, I thought you meant the red curve.
No.
The purple is the measurement from the EHD. The blue is the prediction based on the prior mass knowledge.
But then it is not just widened as it would be just by resolution. It also shifts a little, right?
We do not. So two different things. The blue one is the prediction using the full error distribution of the mass measurement. The purple one knows nothing about the mass measurement of the EHD, it's just the measurement from the EHD.
But it has telescope resolution, right? It has
telescope resolution, yes. The fact that they are on top of each other, or next to each other, or statistically consistent with each other, means that the predicted one given a different set of observations and the measured given the EHD observations are in agreement with each other.
Well, in agreement, but if you take blue curve and just spread it with resolution, you get a little bit different curve, right?
Correct. So it does. Of course, but
that's what I'm asking.
You're exactly right. So actually, in this particular case, this does not peak exactly at 0, but it is whatever 0.1 0.03 plus or minus 0.17 or something like that, which is that difference between the two. Exactly right. Which of course you wanted it, right? You don't want the two that are completely independent to be lined up that well. It would have been too suspicious otherwise.
Okay.
Thank you. So, as I said, we did that to perform a null hypothesis test of general relativity. But what if we want to go a little further? Now I'm a little concerned about the time. Okay, I will do something.
Don't worry
quick.
too much about it.
Okay, I will not worry too much about it. So we wanted to go a little more and say, what do we really learn about the metrics themselves? And the interesting aspect of it is that again, for a long, long time, for more than 10, 15 years, people have tried to parameterize deviations of the Kerr metric, the way that we parameterize deviations of the Schwarzschild metric, but not only thinking about the weak field regime, but also the strong field regime. And what we found, and this is a nice paper by my former students, is that the minute, as expected, the minute you tweak the Kerr metric, it breaks down. Right? There is a reason why the no-hair theorem is a mathematical theorem. The Kerr metric is the only metric that has no pathologies outside of the horizon. And the minute you tweak it, you're going to bring up pathologies. So this is a number of metrics that were known or discovered at the time. And this is just a summary of what kind of pathologies they get. You can have naked singularities, you can have Lorentz violations, you can have time machines, things that if you then try to make predictions for what the shadow would look like in those metrics, will be impossible to calculate, because if a photon hits a time machine, then you don't have an initial value problem anymore, right? You cannot predict where the photon will go. So trying to save those, especially those three initial papers, the initial metrics, two groups, one, my student and mine, Tim Johansen and I, and a group at MIT by Sarah Vigeland, Nico Yunus, and Leo Stein, developed what we call designer metrics, metrics defined in such a way that allow you to tweak, parametrically deviate from Kerr, but without breaking it. And what do we have to give away to not break it? It cannot be a solution to the field equations of general relativity, right? You effectively are not, you have to make sure that you're not Ritchie flat. And the problem is that when you make those designer metrics, they come with incredible complexity. So I showed you the simple Schwarzschild metric. If you want to modify, I'm just showing it to show you the degree of complexity. If you want to modify the Kerr metric in a way that doesn't break down, then you have a number of parameters and functional forms that appear in weird ways to ensure that you don't have any of those problems. And then of course you can do your 1/r expansion in those functions, but it becomes with a lot of complexity. And this is the same, the perturbations to the Kerr metric introduced by the Vigeland and Toll metric and the various gamma parameters. So yes, we do have metrics that allow us to be parametrically different than Kerr, but they are extremely complex. And that made it very difficult to understand. So what is it in the metric that determines the black hole shadow size? And therefore, what is it that we're really measuring? Remember, I showed you in the beginning that this is an important aspect when comparing between tests. So one of the things that we did is that we went fishing, and this is work done by another former student, Leah Medeiros, calculating shadow sizes for different metrics. This is the JP metric as a function of those parameters. And for the other metric, MGBK metric, shadow size as a function of various parameters. And we found two things. One, just like in the case of the Kerr metric, the shadow size seems to depend very weakly on the spin. This the effects of the frame dragging and quadruples seem to typically go hand in hand. But more importantly, the parameter that determines primarily the size of the black hole shadow is just one parameter out of this incredible complexity that we introduced in the metric, that a parameter that determines the TT component of the metric. And drawn by the fact that we have a weak dependence on spin and the TT component of the metric, we actually went and calculated the size of the shadow for any general metric analytically in spherical symmetry. And we found that the photon orbit depends only on the TT component of the metric, and the size of the shadow, which is the gravitational length size of the photon orbit, depends only on the TT component of the metric. And this is what made us believe and start understanding more and more that what we're really measuring is what we're doing with the black hole shadows is putting a constraint on the TT component of the metric, again written in aerial coordinates. So what we can do now is, remember, we have all those TT components of the metric. We can write the size of the black hole shadow in gravitational units. This is the GR1, and this is the infinite tower of terms that you can add. And these metric components do not mean necessarily anything. What you really want to compare now is that metric to the solar system metric. So we can do a transformation to the equivalent post-Newtonian parameters. Remember, we're not doing post-Newtonian tests. We're doing all these other metrics, but then we say what would have been the equivalent post-Newtonian. And all this sum of infinite terms in principle is what we're constraining with the EHT. This is the, plus or minus 17% that I showed you before. You can pick one of those parameters and make them equal to 0. So for the first paper, just to show the significance of it, we made the first post-Newtonian correction to 0. Let's say, suppose that it's a deviation that you would never have seen in the solar system. The limit of the black hole shadow puts a limit on the second post-Newtonian term of order unity. Or if you want, you can start making cross sections, 1 PN versus 2 PN. So throw away the third and higher order, and you see what the constraint is between those two lower order corrections and their of order unity. So what we concluded from all of that is that the black hole shadow measures deviations of the metric, the TT component of the metric in aerial coordinates that depend very weakly on spin. And how you convert it into particular deviations depends on the metric that you're using. How does that compare with other black hole tests? That's where I was going to. Nobel Prize in Physics this past year, the orbits of stars around the black hole in the center of the Milky Way, the detection of the Schwarzschild precession. This is just a weak field classical effect. So it constrains the RR and the TT component. This is the limit. It constrains to gamma minus beta effectively, but says very little about higher order effects because these are orbits that are 10,000 Schwarzschild radii away. And with the new source that is going to be announced, the black hole image is going to be announced in the next few months, we will be able to compare it directly with that because this is the exact same black hole, the exact same source. But the thing that we cared a little more about is the connection to LIGO. How do our tests compare to that of LIGO? And remember, completely different black hole masses, 10 to the 9 solar masses versus 20, 30 solar masses. And as you already know, what LIGO measures is the gravitational waves during the coalescence of those two black holes. And the gravitational waves show this characteristic chirp as a function of time, which you can think of it as the phase of the gravitational wave evolving as a function of time when the frequency evolves. The way that you do that test during the in-spiral part of the phase is you write a model for the gravitational wave phase as a function of frequency, right? The plot that I showed you before. And in general relativity, with no spins, this model has very precise predictions. What if you have modifications from general relativity? Well, you add a correction to those predictions, and then you can take those corrections to those predictions and you convert them in the equivalent post-Newtonian parameters, a way to compare the two tests between the two of us. Remember, we did with a particular metric, LIGO does it with a very particular measurement, but predicting the equivalent post-Newtonian parameters is a way to compare at the far field, where we can do it independent of gauges, independent of coordinates or anything like that. What was surprising when we did it with a group of LIGO friends recently is these are the limits of the 1 PN versus 2 PN parameters. For the blue and the orange condors are for two of the strongest gravitational waves and that have the good masses to be able to put that constraint. Is look at the parameters of order 5, 10, 20. They are highly correlated even with LIGO, and the orientation of the correlation, for a complete luck reason, it has to do with the masses of the black holes and the frequency of the observations that LIGO is sensitive to, is parallel to that green, which is the degeneracy that I showed you before for the M87 black hole shadow. So for a completely different reason, even though we're talking about very different black holes with different measurements, both the EHT constraints and the gravitational wave constraints produce similar correlated posteriors. But of course, ours are infinite because we have one measurement. They have a full waveform, so you can actually put limits at the end of the day. But most importantly, they're parallel and they're comparable in magnitude. So LIGO and the HT produce really wonderful new results between the two. So putting everything together, this is where I started from, but now I'm going to put some of those constraints that I showed. Solar system tests, we do post-Newtonian constraints. Pulsar tests, I didn't show any of that, but this is how we do the types of tests that we do with pulsars. One part in a few thousand there as well. Cosmology, many different ways of doing it. The S stars around the black hole in the center of the Milky Way, brand new tests. LIGO and Virgo, brand new test of general relativity. And the Event Horizon telescopes, brand new test of order unity of general relativity. And when we wrote that paper with that plot with Tessa Baker back in 2016, we only had the solar system and wide dwarf Newton star, double Newton star tests, and we said we really need to look everywhere. I am really happy that, not many years later, we have now a remarkable number of different probes from the cosmological all the way to the stellar mass black holes to be able to probe general relativity in many different places. And this is where I would like to stop today. Thank you.
Okay, thank you very much. Thank you for the presentation. Now let's go to questions. So if anyone has questions, raise your hand. Cecilia, please.
Yeah, this is kind of crazy, but I'm a neutrino person, so all my questions tie to that. So because I'm fascinated by this photon ring and the physics of it. Would there be something similar for neutrinos?
Absolutely.
Cool. I think it would be fun to look into it.
I don't know if you can ever resolve something like that about neutrinos, but it is interesting, of course. I mean, this is pure gravitational phenomenon, and it has to do with the propagation of massless particles, or extremely small mass particles for that matter. The other thing that is massless in general relativity are gravitons. And this is why when you're looking at, I haven't had time to show the ring down of the gravitational waves. After you take two black holes, you coalesce them, and you have the little final black hole ring down. It was known since the 70s that what you're really sensitive to is the perturbations at the photon orbit, because any graviton that is going inwards is going to go into the black hole, and gravitons that's going to go outwards is going to escape, and that's the separatrix. So even though in principle it is the event horizon that is the difference between what you see and what you cannot, in anything that we really do, you're primarily sensitive to the gravitational length size of the photon orbit. And people then ask, why do you call your telescope the Event Horizon Telescope and not the Photon Orbit Telescope? I think that's pretty obvious.
Okay.
But neutrinos will do the same.
That's fun to think about. Thank you.
Mm-hmm.
Okay, next question from Roger Winhurst.
So Dimitri, to what extent does it help that from the radio jet observations of M87, VLBI and so on, you know that the jet is pointing from the center roughly in the 8 o'clock direction? Does that help with determining the spin or other asymmetries you may have?
Very good question. It did not help determining the magnitude of the spin, but it helped us understand and confirm that we understand the origin of the up-down asymmetry. So this is indeed a VLA, VLBA, and 3mm VLBI observations of M87. And you see, you zoom in all the way to the black hole, and you see this beautiful jet that is coming out in this direction, right in this direction. So the orientation of the asymmetry is practically perpendicular to the orientation of the jet. And this is an artistic interpretation of it, which is why we think it is trivial to understand, because if things are moving around the jet, and actually we know now that the jet has to be pointing away, like the angular momentum has to be pointing away from us as opposed to towards us. We wouldn't be able to do that with the jet image itself. Then the things that are coming underneath us are towards us are underneath, the things that are coming above us are above, just like this image shows. And that allows us to be confident that we understand the origin of that asymmetry.
Okay, thank you.
Mm-hmm.
Okay, next question, Edward Chirag.
Hi. No, I don't have a question. I just have a comment, historical comment. I am from completely different field, except for one paper. So I wrote a paper when I was a student 50 years ago, 73 more precisely. And that was what happened when you have relativistic electron, for example, rotating around black hole. So if you have ultra-relativistic electron, it moves by practically the same trajectory as a photon or neutrino or anything else. And the question is, first of all, what are formulas for radiation? And second, this is what we discussed, for how long it will be coherent. What is the length of emission? So it turned out that the length of emission was something like larger than 1. It was logarithm gamma. So the electron can go, many kilometers, being coherent with its radiation, in spite of the fact that wavelength, as you said, a millimeter. So it was a very interesting exercise. At that time, we just did it as an exercise, no idea of any experiment. But we did realize that everything radiated would be on this last orbital orbit, which was completely new idea for us then. I don't know. It was, of course, known since Schwarzschild.
Do you mind sending me that paper? Because I would be very curious. It would be interesting to see at what frequency would that appear, because even if it's not relevant to the millimeters that we're observing right now, it might be a signature that we can poke in a different part of the electromagnetic spectrum, and that would be extremely interesting.
Yeah, we have formulas for radiation. And they have completely different, so the usual synchrotron radiation, if electron goes in a circle, the radiation is proportional to gamma to the 4. But in this case, it was gamma squared. So the fact that they go together and never separated reduce the radiation significantly, parametrically. And it also interestingly that in the ordinary circle, they separate very quickly, but here they go together for many circles. Yes. Yeah, if I have the paper, I'm not sure.
Do you remember which journal it was published in?
Yeah, I hope Inspire will have reference. But,
okay, I will be very interesting to see. As I said, even if it's not relevant for the 1 millimeter, it might be an interesting signature to pick out from someplace else, because that will be another way to probe the exact same photon orbit region.
You said this thing is transparent to photons. What about for relativistic electrons or something? Is it still transparent or there?
It depends on the wavelength. So as you go to smaller and smaller wavelengths, it becomes more and more transparent. At the centimeter, which is gammas of a few, probably then it's not transparent. By the time you have significant gammas, it becomes transparent.
And what about say GeV electrons?
Oh, that will be completely transparent.
Completely transparent.
Yeah.
So it can rotate many times.
Oh yes.
Okay.
Yes, absolutely.
Okay. Any other questions? Now I lost the connection at some point, so I was probably listening to an answer that I almost had myself, but I'm not sure if that was it. You did mention about the presence of magnetic field potentially around those black holes, and of course that may have an effect on the emission and the processes that happen there. So what is the strength of the magnetic field, and is there any substantial particle production? So E plus, E minus production, for example, from the photon emission that goes through the magnetic field. Are the scales relevant even? I probably missed the part that you said, but I'm not sure if I did.
Unfortunately, in this talk, I do not have the most recent highlight. Apologies about that. I can bring it up from a different place. We know about the presence of the magnetic field not only from the fact that the spectrum appears to be synchrotron emission, but also that most recently we have reproduced this image with full polarization information, and you see polarization swirls effectively. You see something that swirls as a polarization there, and that tells you that corroborates the idea. From the fact that it's, there's no significant Faraday rotation, from the fact the emissivity from the synchrotron and everything else, you can combine everything together and figure out what the estimate for the magnetic field is. And in the polarization papers, you can see that for M87 will be of the order of, say, 5 to 10 Gauss, which is a remarkably small magnetic field to generate anything of consequence. So I don't think there is anything that one can do from that. You might get pairs and all sorts of other particles in a different way, and we do not really know if there's no real major calculations for that. That is from the fact that we have GeV protons, and proton-proton collisions give pions, and the pions decay into muons, and the muons decay into pairs, and so on and so forth. So you have a cascade that you can generate. You can get other translativistic particles that come out of the thermal energy of the proton, but not electromagnetically.
Okay, makes sense. Thanks. Any other questions?
This was a great talk, Dimitri. Just for the record, further out in the radio jet, the magnetic field is known to go down to a couple of micro Gauss, right?
True.
But inside, it's only 5 Gauss. It dilutes further out. That's indeed not very strong. So that is too bad. We were hoping for more particles coming out, but
indeed.
Okay. Edward, do you have another question? I see the
I sent this reference to Dimitrios.
Oh,
okay.
But unfortunately, it shows in JET, which is a Russian journal. So
no,
it must have translation. It is 73.
It's 97.
My memory. That's the only thing I remember.
I see. I can always ask Igor for a quick translation.
Sure.
You remember your Russian?
No, the thing is they are
that's
typically
ZP,
translated.
right? Isn't that
Yes.
ZP? Or yeah, so I should be able to find that. I must say that when I was a graduate student, I was working on quantization. I had to read a lot of papers, in the original Soviet, and mathematics is a common language. And if you can I can read Cyrillic alphabet because I'm Greek. So, a lot of things are actually, you can kind of gauge them.
Right. Anyway, I don't see any other questions right now officially, so I want to take at least a moment to thank you again for a very nice presentation. And thanks for taking care answering all the questions.
Thank you very much, everybody. Thank you for coming.